Hello, so in this video we are going to start talking about probability distributions. But before we get there, we need to understand these four terms here. So the first is variability. Now, we've already talked about variability in the context of statistics before. At the end of the day, statistics is all about how things differ. It's the study of variability, right? We see things in the world, they change, and we want to understand those changes. That's what statistics is all about, okay? So a variable then is just simply the thing which can change. It's the thing which we're interested in. So it's simply the characteristic of interest. For example, the height of people, or the weight of a particular type of fish, or the number of people that are attending in the college, right? So these are all characteristics of interest. These are all variables. And you notice these are the values which can change. And we want to understand the changes, perhaps between two different groups, okay? Now, a random variable is still a variable, but it's the variable which results from a random observation or experiment. So as an example, let's suppose we want to understand the average heights of people in the college, okay? So in order to do that, we go out and we collect a sample, and we've talked about the different sampling methods in theme 1, right? So hopefully the sampling methods would be random to ensure they're fair, and we're sure we're getting a fair picture of what's happening here. So a variable, a random variable, is just simply the variable which results from that random observation or experiment, okay? Now, we talked about discrete and continuous before, right? So really what we're doing now is applying this to variables. This is what the next two terms are talking about. So a discrete variable is just simply a value that can only result in specific values within a given interval. Now, they're usually integer values. So for example, if you're talking about number of people, or if you're talking about age, these are classic discrete variables, and you notice that those are examples which can only result in integer values. But it doesn't always have to be an integer. For example, you might be talking about shoe size. Now, you could absolutely have a size 3.5 or a size 4.5, but they're still discrete because they can only result in specific values within a given interval, okay? Whereas continuous variable can result in any value within a given interval. So for example, heights, weights, these are all examples of continuous variables because it's absolutely fine, for example, to have a height of 1.325 meters, right? It's not just like 1 meter and 2 meters, so it's not discrete. It can have any height in between those two bounds, if you like, okay? So let's actually see how to construct then a probability distribution, because the idea is very, very simple and straightforward. So let's suppose we take a sample of people and we ask them, how many siblings do you have? Now, a sibling is just simply a brother and sister. And let's suppose we have an empty table that we need to fill out here for our observations, for our samples, okay? So along the top row, we have the siblings, okay? So you can see here that the top row corresponds to the number of siblings which that person could have. So they could have 0 siblings, 1 sibling, 2 siblings, 3 siblings, 4 siblings, 5, 6 or 7 siblings. And then anybody that has more than 7 siblings will all be clumped together on the basis there's going to be fewer people down this end than there are in the rest of the table. Then underneath, we're going to plot the frequency. That's just simply the number of people that have that many siblings. So let's suppose we have something that looks like this. So we collect our data and we get something that looks like this, okay? So you can see along the top row, I've put my number of siblings. Along the bottom row, I've got the frequency. So how would I interpret this? Well, let's suppose I just pick that one there, okay? That would basically mean that there were 6 people with 2 siblings, because you notice the frequency is 6, the number of siblings is 2. So 6 people with 2 siblings. That one there would mean that there were 2 people with 4 siblings, etc., etc. So the number on the bottom row will correspond to the number of people that have that many siblings on the top row, okay? So how would I convert this from what it is at the moment? So this at the moment would be called a frequency distribution, because it's simply talking about frequencies. Okay, it's simply talking about how many people have each of those number of siblings, okay? So this would be a frequency distribution. My question is then, how do we convert this into a probability distribution? Well, the idea is very simple, okay? So at the moment with a frequency distribution, it simply says, you tell me the number of siblings that you're interested in. So whether it be people with 1 sibling, people with 5 siblings, people with 7 siblings. And then I will tell you how many people have that many siblings. That's what the frequency distribution is doing at the moment. With a probability distribution, on the other hand, we're going to change it so that it's not going to give you frequency. It's not going to give you the number of people that have that many siblings. It's going to give you the probability that you select somebody with that many siblings instead. Okay, so that's really important. It's not going to tell you how many people in our sample had that many siblings. It's going to tell you the probability of selecting somebody with that many siblings instead. So what I'm going to do is I'm going to start off by creating a very, very similar table to what I've got before. So in fact, I'm just going to copy this down below so you can see that it's literally just exactly the same idea. Okay, it's literally exactly the same idea as it is there. Okay, but this time, instead of getting frequencies, I'm going to get rid of all these frequencies. I'm going to change this to probability. So you can almost imagine this as somebody then walks into the room and it says, they select somebody at random. What's the probability of selecting somebody with 2 siblings or 5 siblings? Okay, so how are we going to convert this frequency distribution to a probability distribution? Well, just remember, how do we work out probability? Well, probability, so the probability of an event happening, is the number of favourable outcomes, so the number of outcomes that you're interested in, so favourable outcomes, divided by the sample space. That's how many things can happen in total. So in this case, our sample space is the number of people that we ask, okay? So first of all, let's work out how many people have been asked. So in order to get that, in order to get the size of the sample space, we need to have a look at all of these people. So there were 2 people that had 0, 3 people that had 1 sibling, 6 people that had 2, etc. We just simply need to add all of those numbers together, okay? So it's going to be 2 plus 3 plus 6 plus 4 plus 2 plus 2 plus 1, which makes 20, right? So there's 20 people in total that we asked. So therefore, to get the probability, that goes here, that's going to be the number of people who had 0 siblings divided by the sample space, which is 20, okay? So there's 2 people that had 0 siblings. So therefore we take 2, divide it by 20, that's going to give us 0.1, okay? So that's going to give us 0.1 there. Let me do it in black, okay? The number of people, so the probability of selecting somebody with 1 sibling, well, there were 3 people who had 1 sibling, and there's 20 people in total, so that's going to give us a probability of 0.15. Okay, and if we carry on going through there, so we're simply taking the number of people that had that many siblings, divide it by the sample space, which is 20, and we should get a probability distribution that looks like this. Right, so you can basically see here that I've converted this to a probability distribution. So now I can see that if I walk into the room and select somebody at random, the probability that they're going to have 3 siblings will be 0.2, so 20%, right? So hopefully that kind of makes sense, right? This probability distribution just simply says, well, what's the probability of selecting somebody with that many siblings, okay? Now, if I then change this, so I want to find out what's the probability of somebody having 2 siblings? Well, the probability of having somebody with 2 siblings is going to be 0.3, okay? So that's going to be 0.3 there. Okay, the probability of selecting somebody with fewer than 3 siblings, well, somebody with fewer than 3 siblings, I would interpret that as either having 2 or 0 siblings, or 1 sibling. So therefore, 2, 0, 1 siblings is going to be 0.1 plus 0.15 plus 0.3. That's going to be 0.55. So there's a 55% chance of selecting somebody with fewer than 3 siblings. Then again, if we deal with more than 6 siblings, well, the probability of selecting somebody with more than 6 siblings is either 7 or more than 7. That's nobody. So that's a probability of 0, right? Now, if you have a look at the next one, so probability of selecting somebody between 3 and 6 siblings, okay? So the probability of selecting somebody who has a number of siblings between 3 and 6 siblings, I think this is slightly more confusing, right? Because you notice it says between 3 and 6. So there's 3 different ways, I think, in which you can interpret this probability. You can either say between 3 and 6 siblings, right, okay, that's 4 or 5 siblings. Okay, so 0.1 plus 0.1, that could be 0.2. Okay, so it could be 4 siblings or 5 siblings. Okay, but the other way that you can interpret it is between 3 and 6. Well, what if you wanted to include 3? You know, some people might say, well, if it's between 3 and 6, you could say, well, I can include the 3, the 4, or the 5. Okay, so you could allow 3, 4, or 5. But the other way that you could interpret it as well is to say 4, 5, or 6. Right? And in fact, there is one final way as well. You could also include 3 and 6 as well. So if you say between 3 and 6, you may want to include 3, 4, 5 or 6, right? So you're happy that there's actually 4 different ways in which you can interpret between 3 and 6 siblings. It's not very clear. Now, as a mathematician, this is a nightmare, right? The whole point of mathematics is that you write things and you interpret things in a very clear way. It's very clear what you mean. But here, it's really not, okay? It could be any one of these 4 things. So what we need to do instead is come up with some generalization. We need to come up with some notation which helps it make it clearer. So this is the notation we're going to go with. We're going to basically say, instead of writing the number of siblings every single time for our random variable, what we're going to do instead is just give it the capital letter X. The capital letter X, and it could be any letter, but as long as it's a capital letter, that's going to be the actual random variable. So in this case, we're going to say X is the number of siblings. So we don't have to write number of siblings every time. We just write X instead, okay? But then the outcome of that probability, or the value of that random variable, will be the lowercase letter of whatever we choose. So if we choose X up here, then the lowercase letter x will represent the value of the random variable. Okay, now it could be y and y or z and z, it could be whatever random variable you let it equal, but as long as the capital letter is the actual random variable, that's the entire set of outcomes, the sample space if you like, and then the lowercase letter is a specific value of that random variable. So as an example, I've now said that x is the number of siblings. Okay, so I don't have to write number of siblings every single time. Okay, I could just simply say, right, whenever I see x, I just mean number of siblings. And I've just said the lowercase letter x would be the specific outcome. Okay, so x, and I could say it could be equal to x. Now what that basically means is that the number of siblings could be equal to some specific value. For example, I could say that x equals 3. That would mean that the number of siblings would be equal to 3. Or I could ask, what about x is greater than 4? That would mean that x has got to be more than 4 siblings. Or I could ask that x has got to be less than or equal to 2. That's got to be less than or equal to 2 siblings. So 0 siblings, 1 sibling, or 2 siblings, right? So now we're being specifically clear. So if I now say between 3 and 6 siblings, I can now be clear because I have notation which makes it clearer. So I can say, right, okay, I want the probability that x, my random variable, has got to be between 3 and 6 siblings. So x has got to be between 3 and 6. Then it's up to me whether I want to include the 3 or include the 6 or just have it strictly less than. Okay, so I could, for example, do that, okay, which would mean, well, 3 and 6, but not including the 3 and 6. Okay, so that's going to be the probability that x equals 4 plus the probability that x equals 5. Okay, but if I happen to write this down instead, then I'd also have to add in the probability that x equals 3. Okay, and if I'd also add in the 6 as well, then I'd also have to include in the probability that x equals 6 as well as that. Okay, so you notice that by including this notation, having this handy notation down here, where x is the value of the random variable and lowercase letter is going to be the value of that random variable. So x is the actual random variable itself, the lowercase is the actual value or the outcome of that random variable. Now I can be really, really clear about what I mean. Between 3 and 6 is no longer ambiguous. You can actually say, right, okay, I'm including the 3 and 6 in this case, okay? So you can see with each of these things that we've just found, so the probability that 2 siblings, fewer than 3, greater than 6, or between 3 and 6 is 3 and 7, we can convert this using our notation because x is going to be our random variable. And therefore we're going to reflect. So probability that 2 siblings we can write as probability that x equals 2, because remember x is the random variable, the number of siblings. And fewer than 3 siblings is x is less than 3, and more than 6 is x greater than 6. And between 3 and 7, in this case, the 3 and the 7 are not being included. Okay? So you can see here that you're just being really, really clear when you start to use this notation. First look at it, you go, my word, what does that mean? But you'll get really familiar with this. Okay, it just simply is a way of working with the probabilities so that they're clear about exactly what you mean. Okay, and you could absolutely have a go at these. Now have a look at this one. If you're looking for the probability that x is greater than 1.23, you're like, well, hang on a minute. Aren't these probabilities that we calculated up here, aren't they discrete? So therefore, if you want to work out the probability that x is greater than 1.23, you can't actually do that because it's a discrete probability. You can't have 1.23 siblings. But you absolutely can, because what greater than 1.23 means, it's basically the first number which is above 1.23, which you can take. So the outcome which you can take. So greater than 1.23 will just simply mean 2 and above. Okay, so 2, 3, 4, 5, 6, 7, or 7 plus. Okay, so you can absolutely say probability that x is greater than 1.23, even though 1.23 is not an outcome, because greater than 1.23 will just be 2 siblings, 3 siblings, 4 siblings, 5 siblings, 7 siblings, 6 siblings, or 7 siblings, right? So just be aware of that. Even though you might see something weird like that, don't worry about it, okay? Now, we need to talk about sort of things which we're familiar with and how they translate to probability distributions. So we're familiar with, when we're working with data, we're familiar with calculating things like the mean and things like the standard deviation. Those are actually probably the two most important measures from any data set that you can extract. If you look at any kind of data set, and if you look at any data summaries, you will nearly always find either the mean or the standard deviation on there. Okay? So therefore, we need to understand, what does mean mean? What does the average mean in the context of a probability distribution? Because of course, the difference is, when you're working with frequency distributions, when we're working with frequency distributions here, we were actually working with raw data. We were simply saying, this is the number of siblings which they could have had, and this is the number of people. These are the frequencies of the people that have that many siblings, okay? So that's raw data. This first one up here is raw data, okay? So therefore, you can absolutely calculate things like the mean, things like the standard deviation, right? But when you're working with this one down here, this is now a probability distribution. It's no longer working with raw data. It's just simply an outcome, a possible outcome, and the probability of obtaining that outcome. It's not raw data. So therefore, in this case, does mean actually have any kind of meaning? Does the average have any kind of meaning? Well, we will still want to extract that kind of information, but we don't call it mean. Instead, we call it the expectation, because it's simply now changing it, because we're working with probabilities rather than raw data. Because we're working with probability, we're saying, what value do I expect to get? So if I walked into a room with this probability distribution for the number of siblings, what value do I expect to get? That's simply how mean is now being transferred, okay? So in which case, to work out the expectation, we need to think about how we actually calculate the mean, because the formulas are very, very similar. So let's suppose then that we have data that looks like this. So we have 2, 2, 2, 3, and 4. So this could be number of siblings, it could be heights, it could be ages, it could be anything, okay? But let's just suppose we have data that looks like this. So it's 3 2s, 1 3, and 1 4. Now what I want to do is, instead of working with this as frequencies, okay, so instead of saying that there are 3 2s and 1 3 and 1 4, I want to convert this so that we can work with probabilities instead. So let's just consider, how do we actually calculate the mean? Well, to calculate the mean, we need to add all those values together, all the outcomes together, and divide by the number of people who we've sampled, okay? So in this case, it's 5. So what I'm going to do instead is, instead of writing it as 2 plus 2 plus 2 plus 3 plus 4, I'm going to write it in the context of how many times that number comes up. So you can see here, for example, there are 3 2s in my data set, there's 1 3 in my data set, and there's 1 4 in my data set. You notice these two things are completely equivalent to each other. Okay, all I've basically done is, instead of writing 2 plus 2 plus 2, I've said I've just got 3 2s, so I'm going to 3 times 2, and 1 3, so 1 times 3, and 1 4, so 1 times 4. Now I'm in the position where I can actually start to deal with it in terms of probabilities, because if I break this numerator up, so it's basically, at the moment it's all over 5, but if I can break it up into 3 separate fractions that are each individually over 5, I would get something that looks like this. So you can see all I've done here is, instead of having 3 times 2, I've basically said it's 3 times 2 over 5, or I could write that as 3/5 of 2. Okay, 3/5 times 2. And the same thing here, I've broken that 1 times 3 over 5 into 1/5 times 3. And again, the 1 times 4 over 5, I've broken into 1/5 times 4. So I've simply broken it up into 3 separate fractions. The reason why I've done that is because now I effectively have a probability here, right? 3/5. Look at that 3/5 there. What does that 3/5 actually mean? What does that 3/5 actually mean? Well, it just simply means that there's 60% chance of 2 coming up in my data set, because 60% of my data is 2. And what does 1/5 times 3 mean? Well, it just simply means that there's a 20% chance that 3 comes up in my data, right? And 1/5 times 4, that simply means that 20% of my data is composed of a 4, right? So now I've got a probability that is associated with each individual outcome. Okay, so there's a 60% chance that you'll pick a 2, a 20% chance that you'll pick a 3, and a 20% chance that you'll pick a 4. But you notice that where I got that from was the formula to calculate mean. In fact, this thing at the top and this thing at the bottom, they are still calculating the mean. Okay, but it's just that the bottom one is calculating the mean in terms of probability, and the top one is calculating the mean in terms of the formula for the mean. Does that make sense, right? So now I can start talking about expectation. If you notice the 2, the 3 and the 4, those are the outcomes. Those are the different possible numbers that I could have had in my data. So these are my outcomes, right? These are my values. And then the 60%, the 20% and the 20% is the probability that each of those outcomes is going to come up, right? So therefore I can generalize this to say that to calculate expectation, remember that's working with probabilities, I just simply take the individual outcomes, multiply them with their associated probability, and then add all those together. So let me say that again because that's really important. To calculate the expectation, I simply take each individual outcome, multiply it with the associated probability of that outcome, and then add all of those things together. So if I want to generalize this, what I'm basically saying is that the expectation is given by the sum of the distinct values, sum of the outcomes, multiplied by the probability of that outcome occurring, okay? So in general, I can say this is sum, remember sum just means add together, because you notice I'm adding all these things together, of x times p. If x is the individual outcome, remember we're just using the notation we did before, so capital X represents the random variable, lowercase letter x represents the outcome. So this is the outcome multiplied by their associated probability. Okay, so therefore, if we wanted to calculate the expectation of this particular probability distribution, we would simply need to take each individual outcome, so in this case, the number of siblings, so 0 sibling, 1 sibling, 2 siblings, etc. Take each individual outcome, multiply it with their associated probability, and then add all those things together. So let me show you, okay, to calculate the expectation. So I'm going to write my expectation with a little bit of notation here. So E of x, that just simply means, remember, x is my random variable, and then the E stands for expectation. So the expectation of x. Be aware this does not mean E times x, this means the expectation of x, okay? I could also, because this is talking about a mean of sorts, remember expectation, mean, they're the same kind of thing, just one's working with probabilities, one's working with kind of data, frequencies, right? So therefore I could write it as mu, because that's the sort of symbol that I give to population mean, okay? So because I'm working with mean here. Okay, so therefore, to calculate the expectation, remember, I need to take the outcome, multiply it with their associated probability, then add it all together. So let's see what we get. So first things first, I'm going to take the outcome, which is 0, multiply it with the associated probability, which is 0.1, okay? Then I'm going to add that to my next outcome, which is 1, multiplied by its associated probability, which is 0.15. Then I'm going to add that to my next outcome, which is 2, multiplied by the associated probability, which is 0.3. Then I'm going to add that to the next outcome, which is 3, multiplied by the associated probability, which is 0.2. Then I'm going to keep going. So the next one will be 4 times 0.1. The next one's going to be 5 times by 0.1. The next one's going to be 6 multiplied by 0.05. And then finally 7 multiplied by 0. And in fact, anything more than 7, it's going to be 0 anyway. You can see that from my table. So therefore, I'm just going to add on 0 at the end anyway. Okay, so now all I need to do is stick all of that into my calculator. And if I stick all of that in my calculator, you should get 2.55, okay? So you should get 2.55 as the expectation of x. So 2.55 is going to be the expectation of our random variable. Now just pause for a second. What does 2.55 actually mean? That's our expectation, but what does it actually mean? Well, if you have a look at our probability distribution, it means that if you walk into a room, you take one of these people at random, you would expect that person would have 2.55 siblings. Now, obviously, we've discussed this is a discrete random variable, okay? It can only result in specific values. You can either have 0 siblings, 1 sibling, 2 siblings, 3 siblings, 4 siblings. You can't have 2.55 siblings. But that's not an issue, okay? And actually, this is always the case with expectation. Because of the way which we calculate it, it's a very rigorous way of calculating it, we tend to say, well, actually, if you get a number like 2.55, which, you usually will, then we're just going to say 2.55 means somewhere in between 2 and 3, okay? So if you walk into a room, you take somebody out at random, you would expect them to have either 2 or 3 siblings, okay? That's the way which I want you to interpret that expectation, okay? So that is expectation, right? So that's expectation, which is the equivalent of mean. But what else did we want to calculate? Well, we wanted to calculate as well standard deviation. That's another really common summary statistic which you tend to see when you're working with data. Now, in this case, actually, I'm not going to worry about working with standard deviation. I'm going to work with variance instead, because, of course, the standard deviation is always achieved by just square rooting the variance. Just remember that from theme 1, right? So, in other words, I'm just going to work with variance because I don't have to bother with the square rooting, right? I can just work with variance alone. So let's just work with this. So recall that when you're working with the sample data, this is the formula for variance. And notice that you have the n-1 on the denominator because you're working with sample data, okay? Of course, if you're working with the population measure, right, if you're working with like census data or something, then you would just have the n on the bottom. But because you're working with sample data, it's the n-1. That's your degrees of freedom. And this is the formula. It's basically looking at the average distance from the mean. So the x minus the x bar, square it to make it positive, add them all together, then divide by the number of things which you've got. Then to get the standard deviation, you should have square rooted that, okay? So that's the thing with sample data. Now, here's the thing. We're no longer working with sample data, so there's a couple of adjustments that we need to make. The first is to say, well, hang on a minute, we're no longer working with a sample size. We're working with probabilities instead, right? So there's no sample data, so we don't know how many things have been collected in our data. So therefore, the sample size no longer applies. Also, that sample mean that we've just calculated, well, we've said the mean is a bit like expectation. And the symbol for expectation, we could either write E of x, or we can just call it mu. Both of those are fine, okay? So therefore, we're going to let x bar become mu, and also we're going to say, well, hang on a minute, the sample size no longer applies, but the probability does, okay? So sample size, if you like, is a bit like it's being substituted with the probability of an outcome instead, right? So we're no longer working with frequencies, we're working with associated probabilities. So therefore, the n should kind of be transferred to something like probability, okay? So this is going to be the variance formula, and this is kind of intuitive. So you can still see I've got the sum of my x minus my mean all squared. Still got the sum of my x minus mean all squared. It's just that my mean, instead of calling it mean now, I'm calling it expectation, so mu. Okay? And likewise, instead of having the 1 over n, instead of taking the sample sizes into account, because we're working with probabilities instead, I've just simply replaced this 1 over n with my probability. Okay? Because it's better to work with probability because we're working with probabilities rather than with sample data. Okay? So this is going to be the formula for variance. So let's actually have a go at calculating the variance of this particular data set here then, okay? So likewise, we've got a little bit of a notation thing going on. We could write variance of my random variable, so var of x, if I wanted to, okay? Or I could write it as sigma squared to represent variance as well. So both of those are absolutely fine. So just remember the way to calculate your variance is you take each individual outcome, you take away the expectation, which remember the expectation we've already calculated as 2.55, okay? So therefore, we take that, square it, add them all together, and times it by p, okay? So let's actually do this. Let's actually see how this works, okay? So in order to do this, we need to take each individual outcome, take away the variance, and then square it, and then times it by the probability. So let's see this. So we're going to take the outcome first of all. So the first outcome is 0. We're going to take away the expectation, which is 2.55. We're going to square whatever that is and then times it by the associated probability, which is 0.1, okay? Then we're going to add it to the next one along. So the next outcome is 1. Going to take away the expectation, which is 2.55, square it, and then times it by 0.15, and then so on and so on. So the next one is going to be 2, take away 2.55, square it, and then times it by the associated probability, which is 0.3, and so on and so on and so on. Stick all of that in your calculator and see what you get. Now, in actual fact, there is another formula for variance, which I actually prefer to use and prefer to calculate. So let's actually talk through this. So this is the formula for variance that we've got at the moment. So sum of x minus mu all squared times by the associated probability. So what I want to do first of all is just consider the formula for expectation. That's just simply the sum of each outcome times their associated probability, so sum of x times p, all right? Now, in which case then, if we substitute x for x squared, then that just simply be a case of substituting the x, which represents the outcome, with x squared, which just simply represents the outcome squared, right? If you're taking the random variable and you've got x and x, then the random variable squared, then it should be the outcome squared as well. Okay, so that should hopefully make sense. You can see what I've just made a substitution in pink, right? So therefore, if I also do the same kind of logic, if I have a look, if I change the thing inside the brackets, the thing which I'm taking the expectation of, to x minus the mu all squared, then it should be a case of just changing the thing in pink to x minus mu all squared, where the x in this case is just the outcome for the random variable. Okay, so basically the thing inside the brackets for the expectation is the random variable, and then the thing on the right hand side, the thing which I'm calculating, is the individual outcome. Okay. So, therefore, if you consider that variance is just simply the expectation of x minus mu all squared. How did I get that, I wonder? Well, have a look at the formula for variance up here in the top left-hand corner. I've just simply said that the formula for variance in the top left-hand corner can be thought of, so there's the formula for variance. You notice that formula there and that formula there are exactly the same things. So all I've just simply said here then is that because these two formulas are the same, that can be thought of as the expectation of x minus mu all squared. Okay, that's variance, and therefore I've just said that the expectation of that should be variance. Okay, so that's what I've said there. Now I see a quadratic going on inside the bracket, so I guess first things first, I'm going to expand this quadratic out. So x squared minus 2 mu x plus mu squared, okay? And then I can also say, well, hang on a minute, if I have the expectation of 3 individual random variables, then that should be the same as the expectation of those 3 random variables separately, okay? So the expectation of all of this thing should be 3 expectations combined together. Now, I'm not going to go through the proof of that, okay? It seems fairly intuitive, there is a proof, but it's a little bit gnarly, okay? So I'm just going to follow this logically. All right, so have a look here. Have a look at the end thing. If you notice, I have the expectation of mu squared. Well, remember, mu in this case is just an expectation, right? It's just simply a value. And the value which we got just a minute ago was 2.55. So therefore, if I square that, that's still going to be a constant. And if I'm asking for the expectation of a constant, I'm literally saying, here's a constant. It's not going to change. What's the value I expect to get? Well, it's going to be the constant, right? So therefore, the expectation of a value should just simply be that value. Okay, so from that respect, you notice that I see the 2 and the mu in the middle as well. I can also pull out that 2 mu out the front of my expectation because again, it's the expectation of 2 mu is the expectation of a constant, which should just be a constant. Okay, so the first term stays the same, e of x squared, but then I'm taking away 2 mu times the expectation of x, plus, you notice here I've just got the mu squared because it's the expectation of a constant. Okay. Now, if I do a little bit of kind of substitution here, you notice that I've got e of x in the middle. Well, I know the expectation of x I can rewrite as mu. Like I've got mu's going on elsewhere, why not substitute e of x as mu, okay? So therefore, if I substitute that, I get 2 times mu, or 2 mu squared, okay, plus mu squared here. So if you look, negative 2 mu squared plus mu squared, that should be negative mu squared, right? So I can say that the variance of x, an alternative formula, I could absolutely use this one up here in the top in blue, or I could say it's also the expectation of x squared minus whatever the expectation is squared. Okay, so I could say the variance of x is the e of x squared minus e of x all squared. Okay, that's an alternative formula. So therefore, I could also use that exact same formula on my probability distribution. So instead of using this, I could absolutely go for my alternative formula now, which is going to be e of x squared minus e of x all squared. Okay, so that's my new formula. Now, if you notice that e of x squared, well, e of x squared should just be the sum of x squared times p. And obviously e of x we've already got is the sum of x times p. Okay, so basically it's no different here. It's just that we're reusing what we've already got. Okay, and we're not actually having to come up with any new sort of calculation here. So what I mean by the sum of e of x squared will just be the sum of the square of these values now times by the associated probability. In other words, 0 squared times by 0.1, okay? Plus the next one along, so the 1 squared times the associated probability, plus the next one along, so I'm going to take 2 squared times the associated probability. And then the next one along, okay? So then I'm going to take all the way along, right the way till the very end, so right the way up to 7 squared times its associated probability. Add all those together, because of course that's what e of x squared is asking. Add all those together. But then don't forget, once you've calculated all of that, to do this last one at the end. You need to take away the expectation squared. Well, that's all right. We've already found the expectation squared. It's going to be 2.55. Then we just need to square it. Okay, so that's how you should calculate the variance. Okay, so if you calculate that, you'll find the variance, which should be, regardless of which way you calculate it, it should be about 2.55. Okay, so 2.5475 to be exact. Okay, if I've calculated that correctly. So therefore, in order to find the standard deviation, I just simply need to take the square root of this. Okay, so if I take the square root of this, then I get 1.596. Okay, so that would be the standard deviation. So my expectation, remember I calculated 2.55, and that's how I calculate my variance for my random variable. Now, let's ask ourselves a very similar question now. Let's see if we can change these, let's see if we can change the values of these random variables. So now I suppose, what if everybody had 2 more siblings? In other words, instead of having these outcomes, each person just had another 2 siblings. So x plus 2, 2, 3, 4, 5, 6, 7, instead of 0, 1, 2, 3, 4, 5, 6, okay? So we're just simply taking these outcomes, adding 2 to it. Well, what would the expectation of x plus 2 be? Well, let's think about this. And what would the variance of x plus 2 be? What would the variance of this new random variable be just by adding 2 to all of your outcomes, okay? Well, let's think about this in a little bit more detail. Now, let's suppose at the moment, this is our possible outcomes. You can have 1, 2, 3, 4, 5, 6. Let's suppose these are the outcomes that you can have at the moment. Let's see the transformation which happens when we add 2. Well, first of all, let's consider where e of x and variance of x is on this particular outcome number line. Okay, so the e of x should be roughly in the middle, right? Let's suppose the e of x of that particular sort of distribution should be there. Let's suppose the variance of x is a bit like the spread, okay? Variance, a bit like spread, a bit like standard deviation. So it's just simply asking, well, what's the average spread between the variables? So what we're looking for here is the distance between the variables for variance, okay? Now, what happens if we add 2 to all of our variables? What transformation happens? Well, have a look. By adding 2, all that's effectively happening is that you're just shifting all the values to the right by 2. Right, so instead of having 1, 2, 3, 4 and 5, you've now got 3, 4, 5, 6 and 7. So 1's become 3, 2's become 4, 3 becomes 5, 4 becomes 6 and 5 becomes 7, right? So let's see what happens with the expectation and the variance. Well, are you happy that the expectation must have also moved when we did that shift to the right? So the expectation of x plus 2 should just simply be the old expectation plus 2, right? But you have a look at the variance of x plus 2, can you see that those arrows haven't changed at all? Remember, variance is just simply a measure of spread. It doesn't matter where those values actually are, it's just simply asking how spread out are those values, okay? So in other words, the expectation of x plus 2 should be where the old expectation is, but just 2 further along. It's also being moved with all of those outcomes. So the expectation of x plus 2 should just be the expectation of x plus 2. Whereas the variance of x plus 2 should still be the variance of x, right? We haven't changed the spread of those at all. All we've simply done is change the location of where those outcomes lie on the number line, all right? So in other words, the variance hasn't changed at all. All right, fine. Now if we ask the question, well, instead of moving it like to the right by 2, what happens if they have 3 times as many siblings they did before? In other words, we're taking this random variable and multiplying it by 3. So instead of having 0, you still have 0. Instead of having 1, you now have 3. Instead of having 2, you now have 6 siblings. Instead of having 3 siblings, you now have 9, etc., etc. So I want to work out what the expectation and variance is here. Well, again, here's my outcomes, 1, 2, 3, 4, 5. Let's suppose my expectation is here, and my variance, again, is that measure of spread, okay? Well, what happens if we multiply by 3? Well, effectively, all of these numbers end up 3 times as far away from the origin as they were before. So what happens to the expectation? Well, guess what? That also ends up 3 times as far away from the origin as it was before. So in other words, the expectation of x has moved to 3 times as far away from it was previously. But also have a look at the variance, because now I think the spread of these values have also changed, right? So the variance has also increased. Now here's my question. So we've just established that e of x has just moved to a position which is 3 times as far away from where it was before. So in other words, e of 3x should just be 3 times the old expectation, okay? But here's the question for variance, right? If you have the old variance, you can see that the new variance, because all those values are 3 times as far away from where they were before, the variance has also increased. But my question is, how much has it increased by? Now the temptation is to fall into the trap here and to think, well, if all my values are made 3 times bigger, surely the spread, the distance between those values, should also be made 3 times as big. That is true, absolutely true. But remember that we're not talking about standard deviation here. So the standard deviation between each of these values would be 3 times as far away from where they were before. But because we're talking about variance, and variance is just the square of standard deviation, it means that the variance of 3x should just simply be 3 squared times the variance of x. So the standard deviation of 3x is 3 times the standard deviation of x, but the variance of 3x, because the variance is square of standard deviation, should be 3 squared times the variance of x. So that's really important, okay? And it's a trap which a lot of people fall into. So because I'm kind of drawing these values in here, remember that I'm really kind of illustrating standard deviation on the basis that variance is just the square of standard deviation. So you must remember, if you're working with variance, to deal with the square. By the way, I said at the beginning, the reason why we tend to work with variance, with this kind of expectation and variance algebra, is because the formula for variance doesn't require a big square root at the end, right? So we tend to just work with variance just because variance, standard deviation, they kind of mean the same thing. Just one is the square of the other. And if I don't have to work with the square root, hey, why not, okay? So this is kind of a summary of it. If you take an expectation of a value which you've added some particular value to, so if you know what e of x is, if you then take that random variable x, add some particular value to it, the expectation of that x plus b should be this old expectation just moved b along. But the variance doesn't change because, of course, you're just simply translating all the variables or the values, and you're not simply changing the distance between them. But if you're timesing that random variable by some particular value, then you have to remember that e of a times x is a times the old expectation, whereas the variance of a times x is the square of a times the variance, because you are increasing the distance between the variables, but because you're dealing with variance, it's got to be the square of those distances, okay? So let's work with expectation a little bit more then. So let's work with expectation a little bit more. Let's suppose we have 2 random variables. Let's suppose we have x and y. So x, for example, could be the number of siblings, same as what we had before. But now let's suppose we introduce another random variable, and this could be maybe the height of each sibling. And because it's another random variable, we're going to let it equal a different letter. But it still follows exactly the same rules as we've just seen with random variables. Now, by the way, in this case, x would be discrete random variable because it's the number of siblings, and y would be a continuous random variable, okay? So let's see. What if I wanted to find the expectation of x plus y? In other words, I wanted to take the number of siblings which each person had and add it to the height of each of those siblings. Well, the expectation then will be given as the expectation of the number of siblings, the expectation of my x variable, plus the expectation of my y random variable. In other words, the height of each of those siblings. Now, I'm not actually going to go through the proof. It's fairly intuitive though, right? So the expectation of x plus y should be the expectation of x plus the expectation of y, but I'm not going to go through the proof because it's actually surprisingly gnarly and quite tricky at times. So I'm going to omit it from here, but you're absolutely welcome to go away and have a look at that proof if you wish. So I'm just going to give you this as a factual result, and I'm not going to ask you to prove it, okay? Whereas, what about if I wanted to find the variance of x plus y instead? So I know what the expectation of x plus y is, but what if I wanted to find the variance of those 2 random variables added together? Well, I've just seen that the variance of x, okay, I've just seen that the variance of some particular random variable, let's say the variance of z then, because we're using x plus y, should be given as the expectation of that random variable squared, take away the expectation of the random variable all squared, okay? So we've just seen this. The variance of z should be the expectation of that random variable squared, take away the expectation of that random variable all squared, okay? So in other words, in this case, I'm just simply saying, well, instead of having z, let's suppose we have x plus y. Okay, so you can see here that I've just simply said the variance of a random variable should be the expectation of the random variable squared minus the expectation of the random variable all squared. okay? And in this case, my random variable is just x plus y, okay? Now you have a look here. You see that I've got x plus y all squared. So I think a simple thing to do would be to expand this out. So x plus y all squared, just a simple quadratic, x squared plus 2xy plus y squared. And likewise, because I've got the expectation of those three things, I've just seen if I'm taking the expectation of three things being added together or two things being added together, it should be the expectation of each individual thing. That was on the previous slide, that's given to you, okay? So therefore I'm just taking the expectation of these things, and you notice I've just pulled the 2 out the front there, because if I'm taking the expectation of 2xy, that should be 2 times the expectation of x times y, right? I've just seen that, okay? So now if I substitute that back in, I can replace my expectation of x plus y all squared with this big long expectation. I've just simply expanded it out, separate it into 3 expectations. That's all I've done, okay? Now have a look here. You notice that e of x plus y I can write of e of x plus e of y. I've just seen that. It's on the previous slide. The expectation of 2 random variables being added together should be the expectation of each random variable added together. Okay, so the expectation of x plus y should be the expectation of x plus the expectation of y. And of course I'm squaring the whole thing, so that's the reason why it's in the squared bracket. Now if I'm squaring something, again, simple quadratic, I can expand this out. So the expectation of x plus the expectation of y all squared is the expectation of x squared minus 2 times the expectation of x times the expectation of y minus the expectation of y all squared. You notice I'm just bringing the minus across. So if I expand that out, it should all be positive, but I'm just distributing the minus over that bracket, the negative over that bracket, okay? Now what I'm going to do is I'm actually going to write all of the things with expectation of x's together. So whether it be expectation of x squared or expectation of x all squared, I'm going to group it together. So you see I've got an expectation of x squared there, and I've got an expectation of x all squared there. So I'm going to bring all this together. So I've got the expectation of x squared minus the expectation of x all squared. Similarly with the expectation of y, I've got an expectation of y squared there, and I've got a negative expectation of y all squared there. So I'm going to sort of write that together. Okay, so I'm just simply rewriting it, just not actually changing anything as such here. I'm just simply grouping terms together. And likewise, I've got the expectation of xy there, so 2 times the expectation of y, xy, minus 2 times the expectation of x times the expectation of y there. So I'm grouping those together. Now, you notice the expectation of x squared minus the expectation of x all squared. You may recognize that. That is the variance of x. Likewise, this thing here, the expectation of y squared minus the expectation of y all squared, is just simply the variance, okay? It's just simply the same formulas I've got written down there. So in other words, I've got variance of x and I've got variance of y in my formula. Now this thing here, I'm just going to factor out a 2 for the time being. So I've got 2 times expectation of xy minus the expectation of x times expectation of y, okay? So if I now deal with this, this thing here is just the covariance of x and y. Now, we're going to look at covariance a little bit later on when we look at correlation and regression, but effectively, all I want you to understand by covariance at the moment is it's a measure of how 2 variables vary with respect to each other. So if you have 2 variables and you expect one thing to change as the other variable changes, then the covariance is a measure of how those things change with respect to each other, okay? Now, let's just assume that x and y are independent. Now let's just think. I said that x could be like number of siblings and y could be the height of each sibling. I think it makes sense that those 2 variables are independent. In other words, one thing does not affect the other. Okay, the number of siblings which somebody has does not affect the height of that sibling, right? So they're independent variables. So therefore, there's no dependency on those 2 variables. Now, if you remember that the covariance of xy is simply a measure of how one thing changes with respect to the other variable. So therefore, if we know the value of one of the variables, it doesn't tell us about the value of the other. So therefore, the covariance should just be 0. If one thing changes, the value of the other thing shouldn't change, okay? So its covariance should be 0. So in other words, if I bring this formula back, this negative 2 times the covariance of xy, because they're independent, I don't need to worry about it, it's just 0. So therefore, this is the kind of thing that you need to be aware of. The variance of x plus y should be the variance of x plus the variance of y minus 2 times the covariance of xy. If they're dependent, if one variable depends on the other, you need to have this covariance term. If you don't have dependency, in other words, if they're independent, use just simply the variance of x plus the variance of y. So the variance of x plus y should just simply be the variance of x plus the variance of y if x and y are independent variables, okay? So here we have a summary of exactly what we've just talked through. So we're given this proof at the top, so the expectation of x plus y is equal to the expectation of x plus the expectation of y. We're given that result, we don't need to prove it. But the bottom result, we've just proved that the variance of x plus y should be the variance of x plus the variance of y if x and y are independent. If they're dependent, then you're going to have this covariance term on the bottom here. Okay, so just be aware of that. Okay, so those two results are really important. We will come back to those again. Okay, so at the moment, understanding expectation algebra is a little bit of just sort of theory. It's fairly intuitive results, okay, but just be aware of these results here. Now, if we go back to our probability distribution then, what if we wanted to graph this probability distribution on a graph? Okay, we want to graph this probability distribution. Well, in which case we'd have the x, the outcome or the value of the random variable, along the bottom. And then along the y-axis, we'll effectively have the probability that we'll get each outcome. So if I wanted to convert this probability distribution here into a graph, okay, this is how I'm going to do it. So along here, I'm going to have my outcome, so I'm going to call that x. And then here, we're going to have the probability that x is equal to that particular outcome. So my random variable is equal to that particular outcome. Now, this is really important. We can also call this a lowercase letter f of x, okay? So lowercase letter f of x. Now, what I'm doing here is something called a probability mass function, okay? Now, there are two types. If you're dealing with discrete data, which we are here, it's a probability mass function. So in other words, it's simply a function which will say, you tell me the outcome you're interested in this case, the number of siblings, and I will tell you the associated probability. That's what a function does, okay? So in this case, the probability mass function says, you tell me the outcome, I will tell you the associated probability. If you're working with discrete data, you call it a mass function. If you're working with continuous data, you call it a density function, okay? So if you're dealing with discrete data, you call it a mass function. And if you're dealing with continuous data, you call it a density function. Now, we often abbreviate these to either a PMF for probability mass function or a PDF for probability density function, okay? So remember, a probability function is just simply saying, give me an outcome, I give you the associated probability. And you call it a probability mass function if you're working with discrete data, and you call it a probability density function if you're working with continuous random variables, okay? So in this case, all we're going to do is just simply plot the probability mass function. We're not actually going to come up with a formula that will tell us that. We will do in sort of later distributions, but in this case, we're just simply going to plot it, and this will be the probability mass function for us, okay? So in other words, the height of each bar I'm going to draw is just simply going to be the height of the probability. So you can see here that I've chosen 0, and I'm doing the height of the bar as 0.1 because I'm dealing with a probability of 0.1. Next one's going to be 0.15, so about there. The next one's going to be 0.3, so about there. Next one's going to be about 0.2, so about there. Next one's going to be 0.1 again, 0.1 again, then 0.05 again, and then the next are going to be 0 and 0. So this would be the probability mass function for the number of siblings in our data set, okay? So you notice we've collected data, we've converted that to probability, and you can really quickly and easily see the probability mass function because you're dealing with discrete data as just simply a graph. Now, if you can come up with a formula that will tell you this, then that's fantastic, okay? But from here, that's fine. All right, fine. Now, what if I wanted to find out a cumulative probability? In other words, I wanted to find out a probability like this, the probability that x is less than or equal to some particular value. That can sometimes be really useful, okay? And we will deal with cumulative probabilities later on, particularly, for example, in theme 4, when we're dealing with things like the normal distribution. So if you're looking for the probability that x is less than or equal to 2, you're simply asking, what's the probability that I have less than or equal to 2 siblings? So in other words, 0 siblings, 1 sibling, or 2 siblings, okay? This can be really useful. So you're basically considering all of the outcomes and their associated probabilities up to the one that you're particularly looking at, in this case 2. Okay. Now this is really important, okay, and it can be really, really useful. So again, we give this a special notation, okay? If, for example, we wanted to find the probability that x is greater than 2, we might want to find 1 minus that. So this is an important sort of feature. For the cumulative probabilities, it can be useful to find complementary probabilities and also probabilities between specific ranges, okay? So therefore, the probability that x is less than or equal to 2, the cumulative probability, we give a special name. We call it a CDF. So a CDF stands for a cumulative in other words, all the values up to that point, distribution function. Okay? And what it simply says is that it's the probability that x is less than or equal to some value. Okay, so that's what the cumulative distribution does. It basically says, find me the starting outcome you could have and find me all of the different possible outcomes up to the one you're interested in, okay, and add all those probabilities together. Now, because it's so important, we give it a special name. Well, look, we've already used lowercase f to represent the probability mass function or the probability density function. So therefore, the cumulative distribution function is given with a capital letter F. So that's really important, okay? For the PDF or the PMF, probability mass function or probability density function, in other words, the function which will just simply say, you tell me the outcome and I find the associated probability, we say that's a lowercase letter f. So that's just simply the probability that x is equal to one particular outcome. Whereas for the CDF, for the cumulative distribution function, we give it the capital letter f, and it's just simply the probability that x is less than or equal to every value up to that point. Okay, every value up to that point. So for example, if I asked for f of 3, that would simply be the probability that x is less than or equal to 3. In other words, the probability that x is equal to 0, plus the probability that x is equal to 1, plus the probability that x is equal to 2, plus the probability that x is equal to 3. Okay, so that would be the example of the CDF, the cumulative distribution function for f of 3. So here we have a summary of exactly what we've just looked at. So if you're looking at the probability mass function, it's the lowercase letter f, and it's just simply the probability of getting an individual value, an individual outcome. So the probability that x is equal to some value, okay? If you're looking for the cumulative distribution function, that basically says, okay, f of x, and you notice that it's looking at the capital letter F as opposed to lowercase letter, is just simply all of the values, all of the outcomes added together up until that particular value. So it's the probability of consecutive values, okay? Now the reason why this is particularly important, for example, if you're looking at the probability that x is greater than 2, okay, that would just simply be 1 minus the probability that x is less than or equal to 2. So cumulative distribution function is a really important and useful kind of function to have in your back pocket when you're working through these distribution functions, okay? So for example, if you're trying to work with something like that, that'll just simply be 1 minus the cumulative distribution function of whatever you're looking at, okay? So in other words, you're just simply adding all of those consecutive values together. Now, let's suppose we do an activity, and usually if I was in a class, I would get people to roll dice and actually do this activity, but I think you can kind of visualize it and see what's going on here. Effectively, I'd get you to roll a fair 6-sided dice, and I'd get you to roll it as many times as you can within a 5-minute period, okay? And then all you have to do is just simply record the frequency that each of these outcomes comes up. So the number of times that 1 comes up, 2 comes up, 3 comes up, 4 comes up, 5 comes up, and 6 comes up, okay? And then we're going to use a bit of notation. So we're going to say, okay, in this case, our random variable x is simply the score on the dice. And you then need to create a probability distribution for x, okay? So you need to find the probability that x is equal to that particular outcome, okay? So the probability that x is equal to 1, 2, 3, 4, 5, and 6. And then I'm going to ask you to plot the probability mass function. Well, this is usually, when I get people to do this activity, this is usually what they get. So when they find all these individual probabilities, and you notice that the probabilities along the bottom are not the probabilities you always expect. So just think about it. If I asked you just straight off the bat, what's the probability of getting a 6 on a dice? Or what's the probability of getting a 2 on a dice? Or what's the probability of getting a 3 on the dice, right? You should say 1/6, because one of those sides is the thing I'm interested in, and there's 6 possible sides I could choose from. So it should be 1/6, or about 0.17%, okay? Oh, sorry, 0.17 or 17%. But you notice that because we're doing this as an experiment, so it's an experimental probability, these probabilities will nearly always be slightly different and slightly off. And if you're interested in me actually going through this activity in class, I've got a video on my YouTube channel which you can go and have a look at on my uniform distribution. But effectively, I get them to plot it, and I collect all the class data together, and you should get something that looks like this. So this is the probability mass function. This is f of x. And you can basically see that I've got the outcomes along the bottom, the probability of that outcome along the left-hand side, along the y-axis, and all of these bars are relatively the same size. Okay, they're all relatively clustered around 1/6, and that's how it should look. Okay, so if I wanted to describe the distribution in words, what I'm literally saying here is that the probability of the outcome, so each outcome, the probability is exactly the same. Okay, so the values x equals 1, 2, 3, 4, 5 or 6 all have the same probability of 1/6. Okay, and you notice that the probability is 0 for all other values of x. This is really important because we're dealing with discrete random variable. We can only take the values 1, 2, 3, 4, 5 or 6, which means that if I wanted to find the probability that x equals 2.73, I could still do that. It would be 0. Okay, because any other value apart from 1, 2, 3, 4, 5 or 6 is impossible to achieve on a dice. So therefore the probability has to be 0. And you can see that from my probability mass function, yeah? So everywhere else on these bars is always going to be 0. So therefore, if I wanted to write this as a function, so f of x, remember, is my probability mass function, which is the probability that x equal to some particular outcome, okay? If I wanted to write this as a function, I have two cases. If it's 1, 2, 3, 4, 5 or 6, if my outcome is 1, 2, 3, 4, 5 or 6, the probability is 1/6. Otherwise, the probability is 0. So I can do this using a stepwise function like this, okay, or pairwise function it's sometimes called. So you can see here that the probability is given in two cases. So it's kind of like the probability is equal to this. It splits into two cases. Number one, the first case, is that it's equal to 1/6. Okay, so the first case is that it's equal to 1/6. And that's if all the values are 1, 2, 3, 4, 5 or 6. So if you have a value of 1, 2, 3, 4, 5 or 6, take the value as 1/6, as that's the probability. Otherwise, take the value of 0. So that's how to read that function off. Now that is a probability mass function. So remember in the last kind of part, we were looking at probability mass functions simply from the perspective of graphs. That's fine, okay? Graphs are incredibly useful for interpreting the probability mass function. It simply says, you give me an outcome, I'll give you the associated probability. And you can do that absolutely fine from a graph. But there are also other ways of writing probability mass functions. You can absolutely write them as a function like this. So in other words, the function of x, 1, 2, 3, 4, 5 or 6, it's 1/6, otherwise it's 0, okay? So if you wanted to complete the table, we'll have a look. This is my probability mass function, okay? So probability mass function, I've got my outcomes and the associated probabilities. That's also a probability mass function, that's my distribution. If I want to complete this distribution table, the cumulative distribution function, well here would be the number, so the probability that x is less than or equal to 1, okay? Well that's just going to be 1/6. But then here will be the probability that x is less than or equal to 2. So that would be the probability that x is equal to 1 plus the probability that x equals 2. So that would be 2/6. And then 3/6, 4/6, 5/6, and then finally 1 at the end, okay? And if I was going to plot the graph, you get something that looks like this. So basically the probability goes up by 1/6 for every single outcome. Now you notice that it's not a kind of stop and start graph. It is a continuous graph all the way through. So because you notice that if I wanted to find f of 1.2, which would be about there, right? I could still do that. That's simply asking what's the probability that x is less than or equal to 1.2? Well, that would just simply be the probability that x is equal to 0 plus the probability that x equals 1. Okay, so that would still have a value of 1/6. Okay, and so on and so on. So just notice with the probability mass function, it was kind of discrete bars and everywhere else was 0. Okay, with the cumulative distribution function, it actually is continuous all the way through. And in fact, from then on afterwards, so for 7, 8, 9, 10, 11, it's always going to be 1, and anything before 1 is going to be 0. So it's a continuous function here. So here we go then for homework, for your weekly task, which I want you to upload to Flipgrid as usual, okay? I want you to try and find the expectation and the variance of the distribution that we've just looked at, this uniform distribution. So this distribution here, okay? This distribution here, which you've got as the uniform distribution. Reason why it's called uniform, by the way, okay? Uniform means the same. Okay, if everything is uniform, it means the same. In this case, the probabilities are all the same, therefore it's got to be a uniform distribution, okay? So I want you to find the expectation and the variance of this uniform distribution that I've just found, okay? So if I want to find the expectation and the variance of the uniform distribution, there's the probability mass function. I want you to find the expectation and the variance. Please upload it to Flipgrid before the next lesson.